Hello, I would like to welcome you to this session about accelerating value for large mainframe migrations to AWS. Some companies and institutions still have mainframes. At AWS, we are very fortunate to assist many of these organizations modernize their mainframes with AWS Cloud. We help them to better leverage the unique value and the differentiated benefits AWS can offer. We work on mainframes of all sizes and all types. That means we also work with large or extra large mainframes. And interestingly, discussions around migrating large mainframes can go in many different directions, sometimes in opposing directions. So we have to focus on what's most important and strategic to the customer business. When we discuss with IT executives and business leaders, we observe their objective is often to maximize the cloud benefits in the least amount of time while keeping risk under control. Major AWS cloud benefits include cost reduction and agility. Then there are questions coming up such as, how can we get AWS cloud value from our large mainframe? How can we migrate my complex large mainframe? How fast can we go? For how much benefit and how much risk? These are some of the questions we will address today, especially around how to balance large mainframe migration speed, value, and risks. But before we answer these questions, let me introduce myself. My name is Phil Devalens. I'm a principal solutions architect focusing on mainframe and legacy modernization to AWS. I help customers and partners globally with their mainframe initiatives. As we typically do, let's start from our customers. We have completed numerous migration and modernization projects from mainframe to AWS. We can see customers are from a variety of industries such as financial services, public sector, travel, or retail. They are mostly large organizations, with a good percentage of them having large or extra large mainframes. We recognize mainframe migration is complex, so we invest in making sure we reduce the risk while increasing the efficiency of the tools and practices we use for migration. Interestingly, a large mainframe is like a small data center by itself. And we have a large experience migrating data centers to AWS, so we reuse many large migration best practices for mainframe migration. These best practices cover many aspects of a large migration, such as skills transition, operating model, security and compliance, technical approach, etc. In summary, we keep building on this migration success to enhance the tools and practices better aligned with our customer priorities. So now, let's dig into some of these practices. Before we get into the large-scale mainframes, let's look at the mainframe migration strategies for any mainframe, or for any mainframe workload. You may have seen previously the 6 Rs or the 7 Rs migration strategies for distributed x86-based servers. It's different from mainframes. There are two main reasons for the differences. First, we have different hardware architectures between mainframes and x86. And second, we have different types of toolset for migration. So for mainframes, we have 3 strategies which lift and reuse the existing mainframe application code and data. So you can see those 3 strategies are on top of this diagram. We can see first hardware emulation, second middleware emulation, and third automated refactoring. These 3 all reuse code and data and guarantee functional equivalence. Because these first 3 strategies reuse code and data, they have no manual code development and they reduce the risk and accelerate the migration. We'll talk more about these strategies in the presentation. Then, towards the bottom of this diagram, we can see the repurchasing and the re-engineering strategies. These introduce manual code development, new data definitions, new tests, and take a longer time. Manual work increases the risk, increases the duration, and typically inflates the project cost drastically. At the bottom left, in gray, we notice the retain and retire options. We have seen some customers retiring a mainframe application while still moving and archiving the corresponding data onto AWS. It makes this data available in case it becomes useful in the future. These strategies all have their pros and cons, their preferred use cases, and they are all under consideration when we plan mainframe workloads migration. We'll see how we use these strategies in the context of a large mainframe migration. Now let's look at a large mainframe. What are some of its key characteristics? A large mainframe complex is typically composed of 2 or few machines in parallel. It's also called a parallel sysplex. Customers with extra large mainframe infrastructure can be composed of multiple sysplexes running side by side. Each mainframe machine is loaded with hundreds of processors, tens of terabytes of memory, and plenty of I/O capacity. That allows each machine and a sysplex to process large quantities of program, data, and transactions for numerous users. If we look at a mainframe sysplex with two machines, such as the one on this diagram, we'll notice many workloads stacked up together, mostly using vertical scalability. It's not like a distributed x86 system, where typically we see one application or one component per server. And the mainframe is designed to stay available and reliable with this many collocated workloads. For example, mainframes have a workload manager responsible for prioritizing resources allocation to whichever workload needs it the most. A workload is a set of programs, middleware, data stores, and resources executing a cohesive set of business functions. For example, one workload can support payments, while another workload supports account management, and another workload executes orders management. A workload often has one data store, for example, DB2 or vSAM. It's often supported by one transaction monitor, such as CICS. Each workload can use a different technology stack, so it's common to see a workload with COBOL, CICS, and vSAM or DB2 data. But another workload could use COBOL with IMS Transaction Manager and database, and another workload could use natural programs with an AWS database. For historical reasons, many of these workloads use direct memory-to-memory communication between components, programs, and data store. That means they are very tightly coupled. You remember, I mentioned a mainframe is like a small data center by itself. Well, we can see that when migrating a large mainframe, we actually have to migrate numerous more or less independent workloads and applications. And there is no one-size-fits-all for migrating them. Depending on the business and IT objectives, depending on the technical stack requirements, each workload can favor a different migration strategy. Let's look at what happens to a large mainframe when migrating to AWS. Each mainframe workload is migrated separately. That means each workload ends up having its dedicated compute and data store resources on the AWS side. We see on this diagram that some workloads end up using Amazon EC2 instances, while other workloads use containers or serverless Lambda functions. There are three main complexities that we overcome during a large mainframe migration. The first one is to migrate from mainframe legacy proprietary components to modern technologies. For example, changing from index files such as vSAM files to modern relational databases. For example, changing from hierarchical IMS database to a relational or graph database. For example, changing from BMS maps and green screens to user-friendly web pages. We do this transformation with tools that can either make the change transparent to the application code, or that can make the code adaptations automatically. The second complexity that we overcome during migration is changing from vertical scalability to horizontal scalability. This is especially important for large or extra large mainframes with large capacity needs. They often have stringent performance requirements. Horizontal scalability is what allows meeting or exceeding typical mainframe performance, scalability, and availability requirements. With such a scale-out architecture across multiple availability zones, we increase elasticity and availability. So how do we do such transformation? Here again, the migration tools we use leverage AWS services designed for horizontal scalability. It can be transparent to the application via an infrastructure configuration, or can be done via automated code adaptations. The third complexity that we overcome during a migration is removing some tight coupling for a more agile architecture. For example, removing the COBOL to DB2 type 2 memory to communication to a decoupled stateless compute and data store topology. For example, separating business functions and programs into separate deployment units communicating with APIs or service core. In a nutshell, the large mainframe is migrated workload by workload, and each workload is migrated into a modern software stack which is horizontally scalable and with decoupled components. This presentation is about accelerating value for large mainframe migrations. So what are some of the accelerators? Let's describe some of them here and compare the technical impact for each of them. On the left-hand side, you can see the mainframe platform, from the physical hardware to the operating system, the middleware or the subsystem, the application and data. All these are supporting the mainframe business functions. On the right-hand side, you can see the various migration accelerators and how components are changed for each accelerator. In blue, what stays the same, and in yellow, what changes. This shows you the differences between each migration accelerator. It also gives you a feel for the nature of the projects and their duration. With legacy hardware emulation, the hardware emulator replaces the mainframe hardware. The mainframe operating system and the application stays the same. This is the closest to a lift and shift. With legacy middleware emulation, the middleware emulator replaces mainframe middleware APIs and operating system APIs that are required by the application. This is a porting of the application, where much of the application source code is recompiled without changes. But for change dependencies, there are some necessary code adaptations. With legacy automated refactoring, the code, data, and dependencies are automatically converted to a modern language, data store, and frameworks. It guarantees functional equivalence with the same business functions. On the right-hand side, modern middleware replatforming only applies to modern languages, middleware, and runtimes, which are available across mainframe and x86 systems. For example, it applies to Java, PHP, and relational databases. It allows for reuse of the application code and databases. Looking at these accelerators, the two most popular approaches with our customers are the middleware emulation and the automated refactoring. Let's take a step back and think about why customers are migrating large mainframes to AWS. The two main reasons are, number one, increasing agility, while number two, reducing cost. And if we dig deeper, there are many other business and IT benefits expected from migrating to AWS Cloud. The good news is the migration accelerators enable the majority of the desired AWS Cloud benefits while reducing the risk. So let's review some of that value. First, by virtue of being deployed on AWS and following well-architected best practices, workloads benefit from AWS high quality of service. This is very important for mainframe workloads. High security with extensive security controls and services. High availability with availability zones and workloads spread across isolated data centers. Scalability with numerous instance types and horizontal scalability. Cost optimization with pay-as-you-go and right-sizing. If we use the middleware emulation accelerator, we'll add more value. For example, we can scale out with auto-scaling and elasticity. We can modernize legacy data formats into a relational format for enabling data analytics. We can use AWS managed services for the databases to reduce the administrative task and increase reliability. We can introduce a continuous integration and continuous delivery pipeline. This increases development velocity. If we use the automated refactoring accelerator, we introduce more value by modernizing the technical stack further in an automated way. For example, we can decouple programs and make the deployments more modular. We can increase application agility by creating services or microservices. We do so via program extraction or function extraction. So not only the accelerators get the migration move quickly, provide cost savings quickly, reduce the risks, but most importantly, they deliver the majority of the expected AWS Cloud value in the short term. We often get questions about automated refactoring, about what it means and what it entails. It's an exciting space where we see more and more innovation from software tool vendors. First, refactoring means we restructure an application or a system without changing its external behavior. That means we keep functional equivalence. And because we use automation, we accelerate the transformation speed and reduce the risks. Automated refactoring is not a manual rewrite or a manual transformation process. Automated refactoring can happen at the application code level or at the middleware level. Based on human decisions and inputs, tools or components automatically transform the system structure, preserving the business functionality. It's not just one transformation type, but many capabilities providing value in several dimensions. So let's see some of the capabilities available with automated refactoring. One well-known option is code conversion and refactoring, where, for example, COBOL code is converted to Java and refactored for code quality, maintainability, and modularity. Another popular option is data format conversion. For example, from legacy VSAM or QSAM to relational. This enables new database use cases. Another option important on the cloud is transforming from stateful to stateless compute, following 12-factor app best practices. That allows horizontal scaling for higher availability, elasticity, right sizing, and pay-as-you-go. With the need for more application agility via decoupling, we see more and more vendors providing features for API enablement and services extraction. Automated refactoring also allows choosing various compute types, including containers or serverless, or choosing AWS managed services such as Aurora or RDS. Such refactoring gives choice for more value based on the workload's characteristics. Now that we know more about the migration accelerators types and values, how do we use them? For a large mainframe migration, we typically start with the discovery and inventory of all the workloads that are running. Ideally, the accelerators are evaluated very early with a proof of concept. This way, the accelerators become readily available, proven, and off the shelf for workloads migration. Then we analyze which workload is to be migrated first. And we evaluate which pattern accelerator is most appropriate for migration. That's based on the technical requirements and the business objectives. Then we iteratively repeat for the following workloads. Each workload can use a different migration approach. A stabilized application can benefit from one accelerator, while a strategic application can use another type of accelerator. If we look at the timeline, accelerators typically allow migration of a workload within 1 or 2 years for a few million lines of code. That means the majority of the AWS cloud benefits can be realized in the short term. This is in stark contrast with a complete manual rewrite approach, where for a similar scope, it can take 4 or 5 years and be 5 to 10 times more expensive. Also, some studies show that large-scale manual rewrite projects mostly fail. And analysts confirm these observations. For example, in 2019, Gartner said, quote, "In many application modernization cases, the risk, cost, time, and impact of a rip and replace programs outweigh any potential benefits," quote. So it's usually not in the customer best interest to do a slow, risky, expensive manual rewrite, which postpones the cloud benefits. Looking at the timeline again, the accelerators not only give sooner cloud benefits and corresponding business value, but they also enable sooner innovations. As soon as the workload is in production on AWS, we see a wide variety of new use cases popping up. For example, integration with new mobile applications, data analytics and AI ML initiatives, or IoT and voice-based use cases. So if we think again about the IT executives and business leaders who are willing to maximize the cloud benefits in the least amount of time, the accelerators have a clear advantage. We are fortunate at AWS to have great experience with data center migrations and mass migrations. We use this experience and similar principles to minimize the risk of large mainframe migrations. First, start small and scale fast. We don't take a big bang approach trying to migrate a large mainframe all at once within a specific deadline. We want to avoid analysis paralysis. So we take an iterative and pragmatic approach where we will break down the complexity into separate workloads and projects. We start with a relatively smaller workloads from which we build knowledge and reusable assets. This allows us to prove the migration capabilities and processes. And most importantly, it allows us to define the scaling mechanisms and accelerators for migrating the other workloads. Second, we migrate quickly. As we discussed on the previous slides, we maximize the AWS cloud benefits in the least amount of time. Practically speaking, that means using the accelerators wherever applicable. Accelerators have extensive automation to reduce the risk and duration. This way we can secure the business benefits for each workload within a 1 to 2 years time frame. Third, we migrate then optimize once on AWS. With ever-changing trends and innovation, we see that modernization is a continuous journey. This modernization or optimization is facilitated and accelerated by the breadth of capabilities of AWS platform once on AWS. Finally, go build. That means we take a pragmatic and very hands-on approach. It relies on early proof of concepts and pilots. This way, we can prove the technical viability, we can show the quality, and we can demonstrate the speed and tangible benefits early. Now, let's look at the delivery aspect of a large mainframe migration. The migration program spans over multiple years, but each project focuses on one or few workloads. Each project brings measurable and achievable business benefits. The migration starts with a large mainframe discovery and inventory and moves quickly into the first workload plan, including a hands-on complex proof of concept or pilot. This is when the accelerators start being evaluated and tested. The learnings are used for de-risking the workload 1 migration. During workload 1 migration, we build reusable assets and scaling mechanisms, and these are used and confirmed with workload 2 migration. Then this dynamic amplifies, allowing more workloads to be migrated altogether. You can notice innovations and optimizations can start as soon as the first workload is migrated. Now, let's talk about a customer frequently asked questions. What about the quality of service for my mainframe applications? Mainframes often have stringent non-functional requirements. When migrating or modernizing to AWS, we make sure that we meet or exceed these requirements. So you can see in this table some of the extensive features and capability available with AWS for high security, high availability, scalability, and system management. On top of these, AWS also has numerous capabilities for cost optimization and agility. Specifically for large mainframes, scalability is important. We address this need on AWS by first separating workloads into their own dedicated environments. That means they have dedicated compute, storage, and network resources. Second, we use a large choice of compute available, such as EC2 instance types. For example, one EC2 instance can have up to 224 CPU cores. Third, we leverage horizontal scalability, which allows adding as many instances as necessary to process a load. Not only we can do this across availability zones and isolated data centers, but also across regions globally. If you have questions about how we meet specific requirements or about specific features mentioned here, feel free to let us know and we'll be glad to provide more details about them. When migrating a large mainframe, there can be situations where there are remaining dependencies on premises, or dependencies that are still on the mainframe. So if latency becomes a constraint between AWS and on-premises, we can use an AWS Outpost. AWS Outpost is a fully managed service. It extends AWS infrastructure, AWS services, APIs, and tools to virtually any data center or any colocation space or any on-premises facility. On AWS Outpost, we can run EC2 instances, RDS instances, or EKS or ECS containers. Similarly, local zones or local regions can help for latency-sensitive applications. It's something to keep in mind as available options during a large mainframe migrations. Before we conclude this presentation, I'd like to show you where you can learn more about mainframe to AWS modernization. So on this slide, the first link will take you to many articles about customer success stories and migration tools. The second link describes migration options and some of the accelerators' main differences. The third link is a series of webinars on the topic of mainframe modernization. And at the bottom, the last link will take you to patterns and best practices. Now that we've seen the large mainframe migration approach, I would like to invite you to use it. After finding a large mainframe, we can do an inventory of all its workloads. We'll evaluate suitable migration accelerators based on the workload's requirements and business objectives. We'll prove the accelerator's capabilities and value with hands-on technical POCs or pilots. From there, we'll iteratively create a migration plan for workloads and migrate them. We'll make sure we maximize the AWS cloud benefits in the short term. We've seen there is tremendous value in migrating mainframe workloads to AWS cloud, from quality of service to cost savings, agility, or innovation. This value is even larger for large mainframes. So we can unleash and accelerate this value together. Feel free to reach out to us. We'll be glad to help. Thank you.